Hi, Joe. Oh. Hi, Joe.
Hello.
How's it going today?
I'm just doing good. I took a little nap, so
I'm glad you took a nap. One of us will be awake for this.
I usually get like 6 hours of sleep at night, so it's always good to get a nap.
Yeah, absolutely. How you understanding this cup? You doing okay with it?
Yeah, I think I'm doing pretty good. I attempted to do the homework. I pretty much got it done with. So
So you're pretty much going on board with it. It's
yeah.
actually, did you, if you did, yeah, I saw that. I saw that you did the homework. Did you have problems with the second problem?
Second,
That's the one where they gave you the calorimeter, and all you had to work with was the calorimeter constant and to change the temperature.
I think I might have figured that one out because I had to hit the hidden tab sometimes. But
Basically, what happened for that one is they were assuming in the Bohm calorimeter that the calorimetry constant included the water.
okay.
You were the only one that did the problem. I took it away from everybody because it was being solved in a manner that was different from the way I'd been teaching it. So I took it
Yeah, I
away
tried to
from
get ahead
everybody.
on that.
Yeah. So, Ian, you doing okay with this, with the problems on this?
What is it?
Are you having trouble? Are you doing okay with the problems?
For the most part, what was on the quiz that was due this morning? There was one problem I was confused on the quiz.
Was it the wave problems?
Yes.
Okay, that has to do with the subject we're going to get into. I've been spending the better part of I spent the entire period last time just simply dealing with calorimetry problems. I'm going to briefly touch on it. I have to go through Hess's law, and then we're going to get into wave theory. So it's the next chapter that you were supposed to hook onto. Okay, Ian?
Okay, thank you.
Dan, you're doing okay. Dylan, you're doing okay.
Yep. How about you?
Peachy Keen, wonderful. Just happy to be here. Dylan, are you doing okay with these problems?
I think so. I have to look over them a little bit more, but so far I've been all right.
Okay, it's literally speaking, guys, this is just plugging numbers in, and you have this whole big problem that has a whole bunch of numbers. You just have to sort through the numbers and figure out what goes where. That's the major problem with these things.
Can I ask you a question about the homework?
Sure.
It says on Pearson that it's due on the 22nd, but on my
I'll
course.
change it. I'll change it.
All right, thank you.
What does it say? What did it say? I took it, I extended it to next Tuesday.
I think it's the 24th.
It's supposed to be on, I extended it to the 24th.
Yeah.
Okay, I'll give you to the 24th then.
Just the 22nd.
It's in there, Joe. It's in there in Pearson as the 22nd, but I do believe I did extend it.
Okay.
Okay. All right, guys. It looks like we're with it's going to be 6 guys tonight. David, you doing okay with this stuff?
Not the best, but I'm still going at it. So,
well,
up to now, I've been great. So this is like the most difficult for sure.
Well, there's no doubt about it. It was definitely voted the worst subject, worst chapter of my class in the summer, bar none. Okay. I'm trying to do a quick, real easy problem here.
I would actually like, if it was okay, I would like if we could like go over some of the problems, even that we kind of similar to what we had on the test or the quiz that we just had.
Okay. Quiz is closed. I see no problem with doing that. I'm going to stop share for a second. Okay. I'm going to try and share screen. And Okay, I'm here. Submission review. Quizzes. And was that 12 or 13? 12. Okay, properties. Min's here, so that makes 7 guys. Okay. Okay. All right, 47.05 grams of iron were heated to 165.5 Celsius and placed into water in a calorimeter that had a mass of 122.07 grams and an initial temperature of 5C. If the specific heat of iron was 0.449, what was the final temperature of the water? Okay. I'm going to write some things down here, and then I'm going to go back to a PowerPoint. Okay. All right, and let's see, specific heat of water is 4.184. Okay. All right, I'm going to stop share for a second. And I'm going to go into my cheap little one here. All right. It says that my iron weighs 47.05 grams. That it was heated to 165.5, and it has a specific heat of 0.449. The water, on the other hand, weighed 122.07. It started off at 5 degrees, and the specific heat of water is 4.184. All right. The trouble with this one, David, is you got to use a big, long equation for it. And you have to know that the Q of the metal, or the Q of the system, which is the metal, is equal to negative the Q of the water. So if I put a negative sign out here, then on the inside, I'm going to put all of the parameters
Can't see your
for my
screen.
metal. Okay, thank you. Now you good?
Yep.
Okay, up here, Q, negative Q metal equal to Q of water. That makes sense to you, David?
Yeah.
In addition, I know the Q is equal to MS delta T. Correct?
Yeah.
Not saying anything stupid here yet, am I?
No. This is all the equations.
Okay, so I put a negative sign up here to reflect the Q of the metal. The metal weighed 47.05 grams. The specific heat of the metal was given as 0.449. And the question asked for the final temperature, right?
Right.
But I know that it started out at 165.5, correct?
Yes.
That's equal to the Q of my water, which is equal to the mass of my water, which is 122.07 grams, times the specific heat of the water, times, now the key here to this question, what is the relationship between the final temperature of the metal and the final temperature of the water?
didn't it say 5 degrees Celsius that
No,
the
it
water
said
started
5,
at?
said water was 5 degrees before when you started.
Right.
Okay, that's the initial temperature of the water. So I know that it's minus 5C. Okay. But my question, I'll throw it out to anybody. What is the relationship between the final temperature of the water and the final temperature of the metal?
It's the same, isn't it?
It's the same. So for this, I'm just going to put another TF there. Okay. Okay, David?
Yeah, that makes sense. Yeah.
All right. So now I'm going to do this math out. I'm going to multiply 47.02 times 0.449. All right. This gives me a negative 21.111. Don't worry about this sig figs. We'll deal with that later. But look, this is the 47.05 times the 0.449 times TF. Right?
Yes.
So I got a negative times a negative. So I multiplied this times this times this.
Would, yeah, okay.
And I end up with plus 3494. That's equal to. Now I'm going to do the other side. This times TF. 122.07 times 4.184. This gives me 510.74 TF minus 2553.7. Okay.
Okay. Where's the 2553.7 coming from?
I'm multiplying the 122.07 times 4.184 times the 5C.
Times the 5. Okay, perfect. Yes. Okay.
All right.
now
Now, again, the hardest part about this is keeping your signs straight. Okay. That's the hardest part. Remember, we took this negative and made this number positive because we were multiplying it by a negative.
Mhm.
This side stayed negative because it was a positive times a
Negative and
negative.
positive. Okay, got you.
So I got 2554 plus 3494. On the left side, I have 6048 is equal to 510.74 plus 21.11. 531.85 TF. Now I simply divide the 6.048 by that number, and that somehow doesn't come out straight. 6048.
I know how. You did 47.02 instead of 47.05.
I don't think it's
When
gonna
you were saying it out loud. No, it was when you were saying it out loud.
okay. Is it 05?
Yeah, that's what I have written on my paper.
Yeah, I have 05 written on mine as well.
Okay, so you divide the 6048 by the 531.85 and you get literally 11 degrees. David, did you see that?
Yes, that was actually really, really helpful. I wrote all of that down.
Okay, anybody else? It's a hard problem. The math is hard because you got to keep the signs straight for this. Okay. So guys, are we pretty solid on the calorimetry problems? Come on, guys. All right. If a calorimetry constant is not mentioned, assume that the heat loss to the calorimeter is negligible. Fair enough, guys?
Yep.
Fair enough?
Yeah, that seems.
Yep.
Okay, so we're gonna get in, I'm gonna stop share here. I'm gonna go back into the original slideshow. Is this the one? Yeah, this is the one. Do we have any real problems with these? It seems like you guys have got them pretty well down. I'm gonna do one more for you, and that's gonna involve a bomb calorimeter. Okay. Now, up to this point, we've been talking about constant pressure reactions. In other words, the pressure doesn't change. And legitimately speaking, 99% of our reactions are done under constant pressure because we're doing them right on the lab bench, and the pressure outside's not changing. So most of them are done that way. The difference is if we do it in a bomb calorimeter, what a bomb calorimeter is literally we're making a bomb. Okay, we're taking a little capsule, and inside this little capsule, we're going to fill that with something like a food particle. So we're going to put a food particle in here, and we're going to also have a spark that's in there. So it's the food particle plus constant oxygen all in there. And it's going to be put in a chamber. The chamber doesn't change volume. It's surrounded by water. And what we're doing is we're measuring the temperature of the water beforehand and after the reaction happens. We hit the spark, everything goes boom in this little chamber. Volume doesn't change, but the chamber gives off heat to the water. So the temperature goes up. Now that really doesn't mean a whole lot to you, except for this one thing. When we do it in constant volume, instead of measuring the enthalpy, enthalpy only is associated with constant pressure because of that equation I figured out for you the other day. But we're not under constant pressure anymore. We're under constant volume. So instead of measuring the enthalpy, we're actually measuring the actual change in energy. And realistically speaking, that change is very, very, very small. So we don't have to worry about it normally. Still, the same thing. The Q of the reaction is going to be equal to negative the Q of the calorimeter. And that's going to be equal to the change of energy. Simple problem. A Brazil nut that weighs 0.11 grams was put into a bomb calorimeter and
Professor?
it's combusted. Yes, you're not seeing it, are you?
No, we did this one.
You did this one?
Yeah.
Sorry. Then I don't need to go over it again, do I? Thank you, Joe. Are we good with this?
Would you mind going
No,
over
it's
it again?
real quick. Okay. The weight of the water is 95 grams. You have to understand we are measuring the change in temperature of the water. Whatever you're measuring the change in temperature of, that's the mass you used in the calorimetry equation. Water weighs 95 grams. So we're not going to use the 0.11 grams. We're going to use what the water is because that's the one that's changing temperature. We know that the change in temperature went from 19.5 to 26.8. We want the caloric value. So instead of using the constant, the specific heat, 4.184 joules per gram Celsius, we're going to use the calorie. And a calorie is, the constant is 1 calorie per gram degree Celsius. So we're going to put in the weight of the water, the specific heat in calories, not joules, and the change in temperature. It started at 19.5, went up to 26.8. I multiply these three things out My Q of my water is 693.5. Remember, water went up in temperature, the nut lost energy. So the sign for the nut is a negative 693.5. If I simply want to know the kilocalories per gram, then all I have to do is change my calories to kilocalories. Then once I have the kilocalories, I divide it by the weight of my nut. And that ends up being 6.3 kilocalories per gram. If you notice on a side of a cereal box or a side of any food, when they're giving you the calories, this is the way that was computed. Okay? Questions? All right, I need to talk about state functions. And we just happen to have a state function here. Ian, do you like Florida? Ian's gone away for a while. Jackson, do you like Florida?
Yeah, it's all right.
Yeah, that's all right. Yeah, but would you like to get out of Florida every now and again to cool off?
Yes.
Okay, you want to go to Seattle, Washington. Okay, so you decide you're going to take the southern route. You're going to go over here. You're going to go start in Tampa. As soon as I get my arrow, start in Tampa, go all the way along the Panhandle. You're going to stop in Mobile because that's a good party town. Then you're going to really stop in New Orleans. And you're going to spend lots and lots of time in New Orleans. Feed yourself good, get drunk, you'll be fine, Jackson. Then you're going to go through Texas, San Antonio, another good party town, guys. Then you got a whole lot of nothing. West Texas is oblivion, guys. So you're going that way. Then you get to New Mexico. Oh, you're going to find Santa Fe. You're going to get to Santa Fe and you're going to party some more there. Then you're going to go straight up to Denver, go over to Utah through Nevada, get into California, and you are going to go straight up to Seattle. Dylan, you want to get away from Tampa also. Dylan, do you have any relatives in the upper Midwest?
Yeah, I'm from Ohio.
You're from, oh, great. That's a perfect example. What you're going to do is you're going to go up through Atlanta, straight up through Atlanta. Then you're going to hit Chattanooga, fiddle around here. Then you're going to get into Ohio, Eastern or Western Ohio, Dylan?
Eastern.
Okay. You're near where I grew up. Where'd you grow up, Dylan?
About 45 minutes from Zanesville.
Real close. I grew up in Pittsburgh.
Oh yeah, that's close.
Anyway, what you're going to do is you're going to get onto I-70. Then you're going to go straight out here. By the way, when you get to Missouri, if you're ever in Missouri at 5 o'clock and you're heading west, stop, because that sun is brutal. Then you're going to go to Kansas. No, you may not. No, you're going to go from Missouri up to Iowa. You want to avoid Kansas. By all means, you want to avoid Kansas. You're going to go up through South Dakota, hit Montana, Idaho, and then you're going to end up in Washington. Let me ask you this, gentlemen. Is the amount of change of latitude different from the way that Jackson did it or the way that Dylan did it? Is there any difference in the change in latitude?
No.
Is there any difference in the change in longitude?
No.
You started from the same place, you ended at the same place. So you literally moved north the same amount of miles and you went west the same amount of miles. That is a state function. A state function is when you don't care how you get there, you just care about where you started and where you ended. Does that make sense to you all?
Yeah.
Yeah.
Energy is a state function. If we have a 50 grams of water that's at 25 degrees Celsius, the energy of that system doesn't care whether you started off with boiling water and cooled it, or whether you started off with ice water and heated it. It doesn't matter. All that matters is the change of the energy. And that's what we're basically going to be doing in the next few steps. Yeah. So all the change in energy depends upon is the initial and the final energy. We don't care which way, which path it chose to get from the initial energy to the final energy. We just care about where it starts and where it ends. However, guys, you got to understand, not everything is a state function. Work and heat are not state functions. Let's take a battery. A battery, what is it, 12-volt battery? You put that 12-volt battery and you hook it up to a fan and you keep that fan going, and eventually the 12 volts will go away, correct? Correct?
Yes.
So we haven't lost much heat, but we've done a whole lot of work, haven't we?
Mhm.
Haven't we?
Yeah.
Well, let's take that same battery, and somehow that battery has a short in it. And so the power from that battery is getting drained in the form of heat. Both of the batteries had the same amount of energy lost, but they lost it in different forms. The fan lost it in terms of heat and work. The shorted out battery lost it all through heat. Not all functions are state functions, but energy is. Delta E is the same. It doesn't matter whether we were running the fan or whether the battery shorted out. We still lost the same amount of voltage. Make sense, guys?
Yes.
Okay, Hess's law. We know delta H for many reactions, and sometimes it's inconvenient to measure the delta H. Delta H is enthalpy for every reaction in which we're interested. So basically, we are going to send those reactions through different little intermediate steps that we know the delta H for. And we're just going to simply add up all the reactions. Point, guys. When you are doing Hess's law, and next semester, when you go to do entropy and delta G, my lab and mastering does not give you the standards. You have to look them up in the back of your book. I've yelled at them for years on this. They do not give you the standard values. You have to get in your book, look them up, or Google them. In any case, that's just a bit of fair warning for you. All right, Hess's law. The total change of the entropy is going to be N, where N is the stoichiometric number in front of the product, plus the other N, that is the stoichiometric number in front of the other product, minus the stoichiometric number in front of a reactant times the enthalpy of that reactant, plus the coefficient in front of a second reactant times the enthalpy of that second reactant. I know it looks very, very hard here, but it will make sense, believe me, in the next few minutes. So it also says that the enthalpy for the overall reaction is going to be equal to the sum of the enthalpies from the individual steps. So let's try and do a problem. Yeah. Okay, couple things I need to define before we do that though. If you see a triangle H with a small f there, that means the enthalpy of formation. And what that means is that is the enthalpy change for the reaction as it's made from its elements. And those elements are in their elemental form. Second thing we need to define is that the enthalpies of elements in their natural states is 0. So that's why that was defined as it was. Do we understand what an enthalpy of formation is? These are the numbers that you look up in the table at the back of the book in the appendix. The delta H of formation is the enthalpy change for a reaction, for making the compound from its individual elements. And by definition, an enthalpy of an element in its natural state is 0. Standard enthalpies are measured under standard conditions, 25 Celsius, 1 atmosphere pressure. So let's get to a problem. I have dinitrogen tetroxide plus 4 hydrogens making nitrogen and 4 waters. Okay. My enthalpy of formation of N2O4 is a minus 19.5. My enthalpy of formation of water as a gas is negative 241.8 kilojoules per mole. Nitrogen at 25 degrees in 1 atmosphere is a gas. It's a gas now. It's in its elemental form. Its enthalpy is 0. Hydrogen, same thing. H2 is a gas at 1 atmosphere and 25 Celsius. So therefore, the enthalpy of H2 gas is going to be 0. So if I want to get the overall energy change for this reaction, the overall enthalpy for this reaction, I'm going to take my product, my water. My water has an enthalpy of negative 241.8 kilojoules per mole. I'm going to multiply that by 4. To that, I'm going to multiply 1 times 0 because that's the enthalpy of nitrogen. From that, I'm going to subtract 1 times the enthalpy of N2O4 and 4 times 0 since the enthalpy of H2 is 0. If I set it up, it looks something like this. 4 times a negative 241.8 minus a negative 1 times a negative 19.5. I get this number, negative this number, plus that number. This is the overall heat of my reaction. Are we stunned or are we just absorbing it now?
I have a question. So you said that basically the enthalpy of these molecules would be in the back of the index.
Yes.
So like I would look up the N2O4 and it would tell me that within that molecule it's negative 19.5.
Yes.
Okay.
I'm sorry.
That
Can you see these things? You can see there's numbers there anyway,
Yeah.
right?
Right.
Okay. The first column here is delta H, second is delta S, third is delta G.
Okay.
And they're organized alphabetically according to the most prominent element in the compound.
As in like the one that has the most
So like
molecules?
N2O4, no, not the one that has the most molecules. Generally speaking, it's going to be the first one.
Okay.
So like N2O4, you would look up nitrogen to find it. Let's go through another one of these things. I have 2 H2S plus 3 O2s yielding 2 H2Os plus 2 SO2s. I have the delta H's labeled out here. Okay, Joe? Remember, it's coefficient times enthalpy of the product plus coefficient times enthalpy of the product minus coefficient times enthalpy of the reactant plus the 3 times plus the coefficient times the enthalpy of the other reactant. So I want you to tell me how we are going to set this up.
Give me 1 second real quick. All right. Okay, so first you write 2 times the negative 20.6.
Okay, that's,
H2S
Joe, is that a product or is that a reactant?
product. Want reactants first?
H2S, H2S. Look
Yeah.
at the equation. Is H2S a product or a reactant?
Oh, it's reactant.
So we don't list reactants first.
Okay, so product first, okay. And then 2 times the H2O, which is negative 241.8, plus 2 times negative 296.8. You subtract 2 times negative 20.6 and 0 plus 0.
Just exactly like you said. I got 2 times a negative 241.8 plus 2 times a negative 296.8 minus 2 times a negative 20.6. This turns out to be negative 483. This turns out to be a negative 593. This turns out to be a positive 41.2. I add all that together, I get a negative 1036.0 kilojoules per mole. Easy peasy, guys?
I wouldn't say that, but yeah, it's when I write it down, it's a lot easier.
Do that then. We have another calculation. Who said it wasn't easy?
That was me, David.
David, okay, good. Okay, David, you're gonna do this one. I want you to set it up for me, okay?
Okay, so so it would be 3 times negative 393.9 plus 4 times negative 285.8 or is wait, I'm sorry.
Products
of
minus reactants.
Right, so all of that minus the negative 103.85 plus 0.
And you would be correct,
Perfect.
okay? Easy peasy?
Yeah, I get it.
Not so hard, is it? I want to see somebody else try this. Let me see who else is in here.
I don't know if it's really 100%, but I posted a wiki in the comment section that has all the the numbers, kind of the standard empathies for formations at 25% Celsius.
Okay, what? I'm sorry, I just,
look,
my
it's what
screen
you
went
said.
crazy. My screen went crazy a second. What are you guys seeing here? Are you seeing the screen
Pretty
that
much
begins?
what you said was in the back of the book, I think.
Yeah, I thank you, Joe. That's great. Are you seeing the screen that has 3 NO2s up
No,
there?
we see you. We see you.
Your face.
That's it? You're not seeing anything else?
No.
No.
Okay. Okay. That's what I was afraid of. Don't save. Oh, well. Oh, crap. I love technology. I do so well at it. So this stuff doesn't seem all that horrible then. Hess's law anyway.
No.
Okay, I'm gonna throw a curve at you in a second. Okay. I think that was the last one that we did. Do you need one more of these or can we skip it?
My only question is, on the quiz, are you going to give us the amount?
Yes.
Okay.
On the tests, you mean? If I give
Right,
it,
exactly.
if I give it to you in a test or a quiz, I will give it to you. I will give
The
you.
enthalpy
give you
amounts
these
for the
things.
molecules.
I will give you those things. Okay. All right. Now, the other thing I forgot to mention. Do you notice I've been putting all the states in here? Do you notice that, guys?
Yeah.
All right. Do you think that water has more, it takes more heat to make water as a liquid, or does it take more heat to make water as a gas? The enthalpies change. Okay. There is a negative 241.8 for water as a gas. And if it is a liquid, in this case, it's 285.8. So you gotta pay attention to the states of these things. Okay? Are we good with that then?
Yes.
Yes.
All right, here's the curve I gotta go through. Okay. Sometimes you're not going to be given the individual enthalpies. What you will be given is a series of equations, and you'll be given the enthalpies of each one of those equations. But the idea is you're going to be able to add everything in each one of those equations so that things cancel out and you end up with the equation that you want. But there are two rules you have to obey when you are doing this. If you are reversing the equation, the delta H value changes sign. So what I mean by that is, if I have A plus B yielding C, and that's a negative 4 kilojoules per mole. If I switch this around so that C is now the reactant and A and B are the products, then this energy goes from a -4 to a +4. Does that make sense to you?
Yeah.
Okay. Another thing is, if I have 1A plus 1B yielding 1C, and that's 4 kilojoules per mole. If I double it to 2A plus 2B yielding 2C, I double the enthalpy.
Professor?
Should we be seeing your PowerPoint
Yes,
here?
you should. You
Yeah, I was
should.
gonna say.
Thank you. Sorry. Okay. Yes. You seeing it now?
Yes.
Okay.
Yes.
Okay, so if I invert the equation, if I go from A plus B yielding C, and that's a -4, if I change that around so I go from C to A plus B, that changes the sign of my enthalpy of that reaction. Does that make sense? Does that make sense, guys?
Yes. Yeah.
All right, if I start off with 2A plus 2B yielding 2C, and if that is -8 kilojoules per mole. If I divide that whole thing, if I divide this whole equation by 2 and end up with A plus B yielding C, I half the kilojoules. So whatever I divide the whole equation by, I have to divide the enthalpy by that same number. If I multiply it and I go to 4A plus 4B yielding 4C, I multiply the enthalpy by the amount I multiplied the whole reaction by. Those are the only two basic rules that we're doing. And we're going to lead. It's a puzzle, guys. If you like doing puzzles, you'll like these problems. Okay. On top, I have the reaction, propane plus oxygen, yielding carbon dioxide and water. Okay. If I can look at this as occurring in 3 steps, And if I know the enthalpies of each one of these reactions, I can determine what the enthalpy of the overall reaction is. And let's see how we're going to do this. First thing, look at the target. This is going to be the target equation you're going to have to aim for. You want to look at the C3H8. Is there an equation of these three that has C3H8 in it?
The first one.
First one, okay. Is it on the correct side of the arrow? By my asking that question,
Yes.
if it's a reactant in the goal,
It's
Goal.
a reactant.
okay, good. Okay, second question, is the coefficient the same?
Yeah.
So we don't have to mess with it, okay? And since the propane, this is the only one of these three in which propane appears, you're not going to play with this ever again, because if you play with this, you futz this one up. So this one is gold now. Okay, oxygen. Looky here, it's in two different places, okay? That's going to be harder to figure out, so I'm going to leave the oxygen alone. Tell me, is there an equation in which there is CO2 there?
Yeah.
Yeah.
Is it on the right
Second.
side of the arrow? Is it on the
Yes.
correct side of the arrow?
It's a product.
Yes.
Is the coefficient the same?
Yes.
Don't mess with it. Now we're going to look at our last product. Is it up? Does it appear in the last equation?
Yes.
Yes.
Is it on the correct side of the arrow?
Yes.
Is the coefficient the same?
Yes.
Correct.
So we're not going to mess with it. We didn't mess with any one of these equations. Okay? They get harder, trust me. So I didn't mess with any of them. All I got to do is add up the enthalpies of each one of those reactions. I add them all up, and it turned out to be negative 2,220 kilojoules per mole. Now, interestingly enough, remember this was C3H8 plus 5 O2s yielding 3 CO2s and 4 waters. If you look at this, the 3 C's are on the left side of the middle equation. They're on the right side of the first equation. They cancel out. The 4 H2s are on the right side of the third equation. They're on the left side of the third equation. They're on the right side of the first equation. They cancel out. So that when I remove everything that cancels out, I'm given my goal reaction. Let's try one that really, a real reaction. Okay, David.
Yeah, go for it.
All right. My first reactant is C, as graphite. David, is there one of the 3 reactions that has C as graphite?
Yeah, it's the first one.
Okay. Does it appear anywhere else?
No.
So let's work with it. Okay. Is the graphite on the right side of the equation?
It's one of the reactants, yes.
Okay. Is the coefficient the same?
No.
So what do we have to do with the reactant below?
We have to add a 2 in front of the...
We have to double the whole reaction.
Right, double.
So if I put a 2 in front of the graphite, a 2 goes in front of the O2, and a 2 goes in front of the CO2, and I double my hydrogen. So I go from 2C plus 2O2, yielding 2 CO2s, and this now doubled. Okay, thank you, David. Ian, you out there, Ian?
Yeah.
Okay, Ian. My second, this is my target reaction. My second reagent, 3 H2s, okay? Does H2 appear in any one of the 3 reactions that's below it?
Yes, the second one.
Okay. Is it on the right side of the arrow?
Yes.
So we're not going to flip it. Is
Correct.
the coefficient the same?
Yes.
What's the coefficient in the target?
Oh, wait, 3 and 0.
The 3
And
and,
then 0.
no, 3
1.
and what? 3 and 1. So what do we have to do with this reaction?
What was it? Flip it?
Nope.
Wait.
Ian, it's on the same side of the arrow. If it's on the same side of the arrow, we don't have to flip it. But the
Okay.
difference is my target has 3 H2s. My equation only has 1
Oh.
H2.
Multiply it by 3.
Multiply it by 3. So I have 3 H2s plus 3 halves O2 yielding 3 waters. Again, I multiplied my enthalpy of that reaction by 3 to get 857.4. Okay, thank you. Dylan, you out there, Dylan?
Yep.
Okay, Dylan, the last thing on my target is C2H6. Does it appear anywhere in the 3 equations?
In the third.
Is it on the correct side of the arrow?
No.
So I have to flip that reaction. Okay? So if you look, my enthalpy went from a negative 3119.6, it went to a positive 3119.6. Now, Dylan, are the coefficients the same?
No.
So what do I have to do with this reaction?
Multiply it by 2.
If I multiply it by 2, I get 4 C2H6s. Does that equal 1 C2H6?
No. By 1/4. Sorry.
How do I get this, the C2H6? How do I get rid of the 2 in front of it?
Divide everything by 2.
Divide everything by 2. So I'm going to do that, and I get 2 CO2s plus 3 H2Os yielding C2H6 plus 7 halves O2. Don't worry about the halves at this point. Now, for my 3 reactions, I'm going to add everything that's on the reactant side. I got 2C, I got 2 O2s, which is the same thing as 4 halves O2, plus 3 H2s, plus 3 halves O2, plus 2 CO2s, plus 3 H2Os, yield 2 CO2s, 3 waters, a C2H6, and a 7 halves O2. Now, the thing is, everything that is not in my target needs to cancel out. Are there 3 H2s on both sides? I'm sorry, let me subtract that. Are there 2 CO2s on each side?
Yeah.
They cancel. Are there 3 H2Os on each side?
Yeah.
Yes.
Okay, and 4 halves plus 3 halves O2 equals what?
7 halves.
Are there 7 halves on the right and left side of this equation?
Yeah.
So the O2s, the H2Os, and the CO2s cancel out, and I'm left with 2C plus 3 H2s yielding C2H6. At this point, all I have to do is add up the enthalpies, and I end up with a minus 84.9 kilojoules per mole. Are we okay with this, guys? We good?
We'll be given the enthalpies on that problem, correct?
You mean these things?
Yes.
Yes, you will.
And okay.
Okay. What am I doing here? Okay. New problem. I don't know what happened here. Oh, I got it. Sorry, I skipped ahead too far. I have a new problem here. Okay. So, Min, you out there, Min?
Yeah, I'm here.
Okay, Min. My first of my target reaction, my first reactant is CH4. Do you see CH4 in any one of the three equations?
The first one.
First one, okay? It's nowhere else in any of the other equations. Right? You don't see it anywhere
Yeah.
else, right?
Right.
Okay. Now, Min, is the CH4 on the correct side of the arrow?
Yeah, I think so.
Okay. Min, over here, it's on the left side of the arrow, right? Correct?
Right.
Here, it's on the right side of the arrow. So are they on the same side of the arrow?
No.
So we have to flip it. So we're going to flip that first reaction. It started off as that way, as a negative 74.6. When I flip the reaction, that becomes a positive 74.6. Now, Min,
Okay, I got it.
you got it, Min?
Yeah.
Okay, Min, are the coefficients the same?
1.
Both are 1. We don't have to play with it anymore. Okay?
Yeah.
See, Jackson.
Yeah.
CO2 is my second one. Does CO2 appear in more than one of the equations?
Yes.
Well, let's leave it for the moment. Okay? How about the CCl4?
It's in the second equation.
Is it on the right side of the arrow?
Yes.
Is the coefficient the same?
Yes.
Don't mess with it then. Okay? I'm going to keep you there. What about the HCl?
It's in the last equation.
Last equation. Is it on the correct side of the arrow?
Yes.
Is the coefficient the same?
No, you need to multiply by 2.
Okay. I add everything together. Add everything on the left side of the arrow. Keep everything that's on the right side of the arrow. And if I have this, then the C's are going to cancel. What else is going to cancel?
H2.
The H2s are going to cancel. And that leaves me with my equation, my target equation. At this point, all I have to do is add the enthalpies of these three reactions. Are we
Professor,
Yes.
I have a question, but it's kind of like just about like when it comes to a test, do you want us to write like all the steps down?
Yeah,
I could do this in my head in like 3 seconds.
I understand. But
Okay.
okay, let me put it to you this way. To be fair about it, okay, say you had to flip the first one and multiply it by 2. You could do that in one step. Does that seem fair to you?
Yeah, I get you saying.
Okay. But I
Yeah,
would
but we
like
have to show all of the add and cancel.
Do you have to show the things that cancel? It would be nice, because if you made a mistake, then I would do it, because if you made a mistake up here somewhere, then something extra is going to be in here. Okay. If something extra is in here, that means you did something wrong up here and you're flipping and you're multiplying. Fair enough?
Yeah.
Do we need another one of them?
Yes, if you
Okay,
don't mind.
fair enough. I think I've got just one more. Okay? Who just said that they needed help?
Ian.
Okay, Ian. Okay. Now, look at these equations. They're scrambled a bit more than they were before. Okay?
Okay.
So look at, again, if you do these things in a steady state, if you keep on going the steps the same way, you're going to have a lot less problems. Okay? Does C appear in any of the equations?
Yes,
Which one?
the second one.
Doesn't appear in any of the others, right?
Right.
So you're good. Does it appear on the same side of the arrow?
Yes.
Okay. Is the coefficient the same?
No.
So what are you going to have to do?
Multiply everything by 5.
Multiply it by 5. Okay. I guess I don't have this solved. So I'm going to take that middle equation, multiply everything by 5. So I'm going to take the 5 times the 393 as well. Okay.
Okay.
Now, second thing. What else do I have? What's my other reactant?
The O2?
Is that in my target equation?
No.
What's the next species in my target equation?
Hydrogen?
Okay, so do you see hydrogen somewhere?
So the third one.
Is it on the right side of the arrow?
Yes.
So we're not going to flip it.
No.
So what are we going to do to the third reaction to get it to
Times
be
it all
equal?
times it all by 3.
Times it all by 3. And so I'm going to also take the 3 times the 483.5. Okay. Now, last step. Last thing we have to control is the C5H12. Do you see C5H12 anywhere?
Yes. First one.
So what are we going to have to do with that first reaction?
Flip it.
Flip it. When we flip it, that makes the H a positive 32 missing. What is that number?
There's a gray bar there for me.
You got it?
3,244.8.
Okay, now remember, we multiplied this equation by 5, so there are 5 CO2s. Okay, we flipped this one. When we flip this one, there's going to be 5 CO2s in the reactant. They're going to cancel out. Okay, we flip this reaction so that there are 6 H2Os on the reactant side now. Remember, we multiplied this one by 3. So this means that we have 6 H2Os on the left. The H2Os cancel out. The only thing that's left are the oxygens. We have 8 because we flipped this reaction. We have 8 on the right. Multiplied this by 5, we got 5 O2s. Multiplied this by 3, we got 3. We have 8 O2s. They cancel. We have 5 Cs on the left, 6 H2s, yielding C5H12, and that's all. We would then add the heats of reaction then.
Okay, so I have a question with this problem. Basically, what we're seeing is the net ionic equation in the beginning.
Nope, you're not. There's no ions here.
I'm just confused of where like the O2 came into play.
Because we know, okay, we know the heats of reaction of these three reactions, okay? If we can get these 3 reactions to somehow add up and equal this one, then all we have to do is add the heats of reaction, and we have the heat of reaction of the top one.
Okay.
Semi?
That I kind of understand. I understand what I'm seeing. I just the beginning of it and how it broke down to.
Okay. You're given the overall reaction. You don't know what the heat of reaction of this top one is, okay?
Right.
You're also given 3 other reactions that you do know the heat of reaction for. You have to manipulate the 3 reactions that you're given so that they equal this. When the 3 reactions are manipulated so that when you add all 3 of them together, it equals the top one, then you can add the enthalpies together, and that will give you the enthalpy
So
of the top
essentially, we're
one.
using known reactions and known heat to figure out
What
different equations.
Exactly.
Okay, that makes sense.
Exactly. Any more questions about this sort of stuff? If you're having difficulty, I know that I have a video on this. Please, it's either the Organic Tutor, and it probably is the Organic Tutor at this point. Please go and see that, okay?
When you flip,
Go ahead.
when you flip the C5H12, all you do to the H value is flip the sign, right?
Because the coefficients are the same, correct.
Okay.
Okay. Are you seeing? No, I don't think you are. Are you seeing my screen now?
Yes.
Yes.
Okay. Chapter 8. Chapter 8, guys.
Yes.
All right. We're getting into quantum mechanics. How many of you guys liked quantum mechanics in intro? It was something, it was that thing that once you got the click on, once it clicked, it was easier than anything, right? This was the 1s2, 2s2, 2p6. It was that thing. You remember that?
Yeah.
Yeah.
And you remember doing the orbital diagrams?
Sadly.
That is what we're going to get into now, okay? But I have to go through and explain a few things so that we understand why what we're doing is what we are doing. And what we're going to do is we're going to talk about the wave nature of light. That's probably all the further we're going to get tonight. We're going to deal with the particle nature. And we're going to deal with the duality between wave and particle theories. We're going to deal with line spectra, the Bohr atom. And finally, in this chapter, we're going to get into a new thing known as quantum numbers, and we're going to deal with the shapes of the orbitals. All right. And I know, guys, I'm going a little bit over. If you can just indulge me, I would really appreciate it. All right. To understand electronic structure of atoms, you got to understand electromagnetic radiation. And up until the 1900s, there was a theory which involved the classical wave theory. And this was how particles were meant to be moving when we're talking about electromagnetic light or electromagnetic radiation. And to define that, they had to define what waves were. Now, by definition, a wavelength is the distance between 2 crests or 2 troughs of a wave. The amplitude of the wave is equal to the amount that the wave goes in a y direction away from the x-axis. So I just said that. So in classical wave theory, they show that the amplitude of the wave is equal to the energy. And it kind of makes sense. When you're looking at a tsunami, you look at how high the wave is, and how high the wave is how destructive that tsunami is going to be. Now, there's also something called the frequency of waves. And the frequency is nothing more than the number of waves passing a given point in a unit of time. You kind of like may think of frequency as the velocity of the wave. If you have waves traveling at the same speed, the longer the wavelength, the smaller the frequency. And that makes sense because, literally speaking, this particular wave is encompassing 3 of the top ones. So as this one is moving that far, this one has moved 2 wavelengths, this one has moved 3. So the smaller the wavelength, the larger the frequency. The longer the wavelength, the smaller the frequency. Now, when we're dealing with quantum mechanics, the energy is related to the frequency. Greater the frequency, the greater the energy. So, important slide. If you have a long wavelength, you have a low frequency, low energy. Short wavelength, you have a high frequency and a high energy. So waves, just as a little summation, waves have a characteristic wavelength that's defined by that funny looking upside down Y that's called a lambda, and an amplitude which is defined as A. Frequency is the number of waves that pass a point in a second, and the speed is given by its frequency multiplied by its wavelength. If we're dealing with electromagnetic radiation or light, the speed is equal to the speed of light, which is 3 × 10⁸ meters per second. So the speed of light is equal to the frequency, the funny looking V, times the lambda, the wavelength. Now, we have different aspects of electromagnetic radiation, going from small wavelength to large wavelength. We go gamma, X-rays, ultraviolet, visible, infrared, microwaves, radio. As we go from gamma to radio frequency, we are increasing our wavelengths. At the same time, we go from gamma to radio. We are decreasing the frequency. We are decreasing the energy of those particular waves. We also have to understand that the visible will also separate into different wavelengths. If you remember Roy G. Biv, red, orange, yellow, green, indigo, blue, violet. As we go from red to blue, blue has the higher energy. Red has the lower energy. It's an easy way to figure out that UV has more energy than IR. Violet is on the low wavelength part. Red or infrared is on the higher wavelength. IR, longest of the visible. Heat radiations will cause a molecule to bend or stretch. On the other hand, if we have microwaves, the reason microwaves heat up your food is that literally all it's doing is it's putting waves of energy into your food. This is causing the molecules of your food to rotate. And as they rotate, what's happening is they're bending against one another, creating friction, which is creating the heat. Shortwave, things like ultraviolet. Ultraviolet rays these things actually break chemical bonds. There's enough energy in UV to break chemical bonds. And I think I have indulged on you pretty much enough at this point. Okay? So be aware that we're going to be getting into waves. We're going to be getting into quantum mechanics and all that good stuff that entails. Any questions about tonight, guys?
No.
The lab is pure calorimetry. That's what we're doing tonight is calorimetry. So hopefully you'll get there and you'll be ready to fire this stuff away. You guys are understanding. You guys are understanding it a lot better than my morning classes.
Nice. Professor, I have a question. When it comes to C equals V times lambda, what is C and what is V?
C is the speed of light. It's a
Okay,
constant.
and V is the
V
frequency.
is the frequency. Frequency
And the
is, and lambda is wavelength.
and
Okay.
lambda is
If David,
yes.
if we are talking about different types of energy, okay, we are going to use different things to define those wavelengths. For example, when we're going to be dealing with this one a lot because this happens to be the same wavelength that the hydrogen spectra uses. Normally, when we're in UV, we're talking about nanometers, which means that our conversion is 1 meter is equal to 10 to the minus 9 nanometers. Did that answer your question, David?
Yeah, kind of, yeah.
Kind of, sort of.
Yeah.
I tap dance pretty good, don't I?
Once I start to like do the problems and stuff like that, it always flows with me better.
Just to give you a little bit, if anybody's still here, basically this is where we're going. Okay, calculate the frequency of light with a wavelength of 585 nanometers. Well, 585 nanometers, we have to relate this. I'm sorry, there was the equation there. Our equation is the speed of light is equal to lambda times our frequency. Okay, David? But our speed of light is in meters per second. So I have to convert my nanometers to meters by multiplying it by 10 to the minus 9th meters over 1 nanometer. And this gives me the number 3.85 times 10 to the 7th meters. Then I've got my speed of light, 3 times 10 to the 8th meters per second. I'm going to divide it by my wavelength. And I come up with a real small number here. It's a real big number here. And that is my frequency. Okay, David? That's where we're going. That's where we're going. That's where we're going to start on.
What is just on really quick, the S at the end of that?
Seconds to the minus
frequency?
1.
Seconds to the minus 1. Is it because
okay, look at the labels here, David. I've got this label is in meters per second, correct?
Right.
I'm dividing meters per second. I'm dividing that by meters. So the meters goes away. The only thing I have left is being divided by seconds, or seconds to the minus 1.
Oh, okay. Got
that
you.
That is the label for frequency. It's also the label for, it's also a 1 over a second to the minus 1 is something called a hertz. That I get into it in a second. It's just kind of like whether you call something a cc, a centimeter cubed, or a milliliter. It's the same label.
Okay, got you.
Anything else, gentlemen? Well, I will see you at, those of you who are taking the lab, I will see you at 7:30. Those others of you, I will see you on Thursday at 5:30. By the way, if So it behooves you. I told my other class that I'd be willing to get into the class a half an hour early on Wednesday. If you want me to do that, I'll make the same offer to you, but tell me now, okay?
What time Wednesday?
5.
Okay.
But you gotta email me too. Just email me and that will jog my memory, okay?
All right.
Okay?
I got a question once everybody leaves. It's about my grade.
Okay, no problem. Okay, guys. That's all we got. I got only 2 more people. I've only got you and me in here now.
Okay.
Okay?
Uh,
All right, Ian.
So I asked another professor basically with the way I took this semester and how